Hi folks, welcome to chapter 7, second lecture, and overall in our series, the 26th lecture. Yesterday we talked about the, this figure I want. We talked about generation of high AC test voltages. And we learned that single unit uh, with conventional insulation system, that is paper and oil, it was possible till up to 750 kV, and it has increased to 1000 kV with SF6 gas compact system for the generation of high test voltages. But you do need sometimes even more than 2000 kV. People have produced in the world the AC power frequency to the tune of 3000 kV. Why do you need? One thing, 2000 kV would be needed for the already in system 1150 kV transmission voltage, and people are working in other parts of the world on this system of, you can say, in the range of 1200 kV. So the work is going on, and you need more higher voltage for the research activity to be able to develop that kind of a thing. And I also showed you how this can, such high voltages of the order of 1800 and 2000 and 3000 can be produced with the help of cascading the voltage. The output of one stage of cascade is added up in the second stage and then in the third stage. So this diagram, what you see here, this is an improved version of a cascade, and which can produce 2250 kV. The schematic, as you see, there is a slight mistake in this diagram, which I would like to elaborate. The number 2 is actually 1, and number 1 is actually 2. Okay, just make this minor change in the mind or in your notes, and rest of the things are all right. The low voltage winding in 1, as you see it here, this is an outside source, isn't it? And this is being given to initiate the cascading effect. But for the next stages, the primary voltage, this is one, is the primary voltage of the first stage. For the second and third stage, the primary voltage of the transformer is the excitation voltage, number 4, as you can see it there. And there is a provision of balancing winding, number 3, present in all the 3 stages. The only difference is in 1 and 1 and 4 are, you can say, the same thing. In 1, it is provided from outside. In the other stages, 1 is replaced by 4. So this balancing winding, number 3, as you can see, number 3 balancing winding, the voltages are given here in the 3 stages. That is, the concept has been developed in to provide in between the 2 windings, that is the secondary winding, high voltage winding, and the excitation winding. In between, another winding has been introduced, which has intermediate voltage between the 2. That means, see one thing, the input here in stage 2 is 750 kV, as you can see. And the output of the stage 2 is added up, just doubled by cascading 1500 kV. The balancing winding is in between the two, 1125 kV. This has been developed, the concept, to uh, rationalize in the provision of insulation between the two. From 750 to 1500 kV, you would have required very large amount of insulation. So in the balancing winding at intermediate stage of voltage, that is 1125 kV, you have intermediate voltage. So from 750 to first 1125 and then 1125 to 1500. The total insulation has been divided into two, which the one such bulk insulation is then not needed to be provided, and that reduces the size of the equipment. And another important thing in this concept is that the uh, over the core, the windings are given. That means windings are overlapping each other. As you can see the construction, the important part, the windings are overlapping each other. So this is what I wanted to communicate. Just a minute. Yeah, this balancing winding, in order to reduce the bulk insulation, as I just now mentioned, and the rest of the things are same. Yeah, so this is an improved version of the cascading, and yeah, this is one of such uh, high voltage equipment producing 2250 kV using the principle what just now explained. And you see the height, width, size of this giant, as I called it. It looks like a giant, but such equipment are needed if you want to experiment with higher voltages. So that is to give you some idea of what is happening in the high voltage power generation. Now, remaining within the generation of high power frequency test voltage, there is another requirement. The requirement is tuned resonant high voltage AC test equipment. Why do we need such tuned resonant? Resonance, you understand. Resonance means when there is, the ideal condition of resonance is when the capacitive reactance is equal to the inductive reactance. So under this condition, the power factor, power factor of the power factor of the equipment delivering power would be 1. So tuned resonant high voltage AC test equipment. What is this? Yeah, so there are two ways of equalizing the reactance, the capacitive and the inductive reactance. One, you see, why is the need? Let's talk about that first. There are certain equipment which need to be tested with high voltage, having very high capacitance. We know in the whole process, we test the capacitance formed by the insulation, or the insulation forms the capacitance, and it is ultimately the capacitance to which we are applying the voltage. The circuit of the high voltage equipment is actually at open circuit condition. There is no continuous current flowing in the apparatus. Only the apparatus is requiring charging current for the capacitance formed by its insulation. So all the high voltage tests are performed at open circuit conditions. So open circuit conditions, you can say. So when, for example, just think of 500 kV polyethylene cable, which requires something like 2.8 centimeter thick insulation around the conductor in a single core. And if you have to test, say, 500 meters of such cable, you can calculate it. So very high capacitance formed by the cable. And when you apply to the tune of for 500 kV, you may need U0 2.5 to 3 times U0. We talked about U0 yesterday. The voltage may be something like 750 kV to be applied at such high voltage. When the applied to such high value of capacitance formed by the test object, it will draw a lot of capacitive current, the lot of reactive power it will draw. And how can you bring down the reactive power? If you have in the circuit equivalent reactor, the capacitance is being equalized, is tried to be equalized with inductance, that is the reactor. And there are two ways of providing equivalent or making the capacitive and inductive reactances to be equal. One, you provide a variable inductor reactor, variable inductance reactor. That means you can vary the inductance of the reactor physically, or it can also be done under the conditions automatically. Or you can also do one great thing to make XL and XC to be equal. You XL is equal to omega L and XC is equal to 1 by omega C. So if an omega is equal to 2 pi F, if you change F, you change XL and XC. If you increase frequency, XL would increase, and if you increase the frequency, the XC would reduce, isn't it? So you can get an optimum frequency at which omega L is equal to 1 by omega C, that is XL is equal to XC. So you can tune the capacitive and inductive reactance by increasing the frequency of the applied voltage. So that's another way. That is what it is, why it is called the tuned resonant high voltage AC test set. This is particularly the need arose for high capacitive or high capacitance equipment for testing. And yeah, as you can read here, it has been well written. Yeah, I was just thinking, see, I tried to explain things here to you, and unfortunately we cannot have an interaction between us. So in case you don't understand, I would recommend to read from our latest book published last year, by me and Dr. Bharat Singh Rajpurohit. And even before coming here to deliver this lecture, I read my own book. And every time I read it, I must say one thing to myself: oh, you have written well. So why don't you also make use of something written well? I would recommend that too for you. It's not an expensive venture, and it will, if you want to really gain knowledge, it would be advisable to also read the book. Yeah, the necessity I have explained: tuned series resonant high voltage power frequency test equipment arose in particular by the cable manufacturing companies, and then the capacitance and uh, capacitance CT has been taken here of the test object. Uh, a variable reactor is connected on the low voltage side itself. You don't need to connect it on the high voltage side. You can connect it on the low voltage side itself. Winding of the test transformer. If the inductance of the this reactor is tuned to match the impedance of the capacitive uh, load, or you can say reactance of the capacitive load, the capacitive power can be completely compensated. When it is completely compensated, what would be the power factor of the current delivered by the high voltage test generator? It'll be 1. That means it will deliver only the real power, and the magnitude of the current would reduce drastically under such conditions. So there are two ways of connecting the the variable reactor. As you can see, this is a variable this is a variable reactor, and it is connected in it's a single transformer, and the reactor. As you can see it here, the circuitry given, it is uh, applied by a very small power rating regulating transformer, or a regulator. The power can be supplied, and with this connection, this is the test object. So by uh, providing adequate value of the reactor, you can get a reasonable magnitude of the current delivered by the test set. You can also connect two variable reactors, as you can see in the diagram B. Two uh, or more units in series are connected. So these two, this is one and this is the second unit, are connected in series, and the units are identical. They are connected in series to provide the voltage to the test object, and you can again, the primary voltage, or the voltage is supplied by the voltage regulator source, the AC power source, and you get you can reduce, if not 100% tuned, you can increase the power factor towards 1, or say even if you get a power factor uh, to the tune of um, zero point 0.9, the output current would be reduced drastically. If you didn't have reactor here in these circuitries, the total current delivered to the test object would have been capacitive reactance current. The reactive power would have had the characteristic of total capacitive current, and that magnitude of the current would have been very high, and that can be brought down with this tuned. Uh, this is physically tuned. Sorry, Yeah, the equivalent circuit diagram for, just a minute, the equivalent circuit diagram, uh, yeah, uh, yeah, uh, the equivalent circuit diagram for this is a low damped series resonant circuit. The high voltage output can be controlled by a variable AC supply, the voltage regulator transformer, regulating transformer, you call it, or a feed transformer, if the circuit was uh, tuned beforehand. I mean, you can set the variable reactor at a position nearby the capacitance formed by the, or the capacitive reactance formed by the test object, and accordingly you can set the variable reactor to a particular value, and this would give rise to much lower current drawn by the test transformer. The feed transformer is rated for the nominal current of the inductor, and its voltage rating could be very low. Then you might have learned the concept of Q, which I will be just introduce it to you. This is more used in communication circuit, but it has slight relevance here also. It may be seen that it is possible to have series resonance at power frequency. With this condition, the current is in the test object is very large and is limited only by the resistance of the circuit. The waveform of the voltage across the test object will be purely sinusoidal when you are supplying. Then the magnitude of the value magnitude of the uh, magnitude of the voltage across the capacitance C, let's call it to be Vc, will be equal to minus jVxc upon R plus jXL minus Xc. And when XL minus Xc are equal, under the condition when you have put adequate value of inductive reactance or the reactor, XL and XC cancel each other, and then the voltage across the capacitor will be V by R into XC, or you can say XC is 1 upon omega C, so that will be V by omega C R, and V by omega C R as V, that is, you can say 1 by omega C R. This factor is known as Q factor. This is known as Q factor, and 1 by Q obviously will be equal to omega CR. The factor XC by R is the Q factor, that is 1 by omega CR is the Q factor, and of the circuit, I mean circuit characteristic is defined by the Q factor and gives the magnitude of the voltage multiplication across the test object under resonance conditions. This gives the magnitude of the voltage multiplication across the test object under resonance conditions. Therefore, the input voltage required for excitation is reduced by a factor 1 by Q. That means the input voltage to the test set by voltage regulating transformer will be reduced by 1 by Q factor, and the output kVA required is also reduced. Therefore, the total power required by the voltage regulating transformer to give the test set under test conditions, the power required will be also reduced by a factor 1 by Q. Secondary power factor of the circuit secondary power factor of the circuit is unity when XL is equal to XC. So what would you like the power 1 by Q to be equal to very large? Then it will 1 by Q is small, Q is very large, isn't it? The Q is very large. So yeah, correct. Yeah. So for high capacitance and ohmic loads, ohmic load will every conductor, every test object would have. Ohmic load is offered by the conductor in the test object, the metallic conductor. So for high capacitance and ohmic loads with high real power losses, the parallel resonant circuit shown in the previous figure is more suitable. Just a minute. We have to consider in the last figure what we talked about was a series resonant circuit. The series, the second figure, as you see, the resonant circuits are in series. So people thought, why not put the resonant circuit in parallel? As you see in this diagram, in the diagram A, the diagram A as automatic tuned variable reactor and AC resonance test system of 400 kV, as you see it here in this diagram. And the B is a cable drum length under test for showing variable reactor of the at the back is the variable reactor. So cable drum, you can imagine, very thick cable offering very large capacitance, and the test transformer connection, as you see it in this figure 8.1, figure 8, sorry. The tuned variable reactor circuits, series and parallel capacitance cancelled inductor. Series and parallel connected inductor. In this, as you see, the variable reactor, this is variable reactor, this is connected in series, and in this case the same variable reactor can be connected in parallel, and it is advisable under the different conditions the series and parallel connections. For high capacitance and ohmic load, as mentioned, loads with high real power losses, a parallel resonant circuit as shown here. The parallel resonant circuit is more suitable, and both these series and parallel circuits can be made in the same apparatus, same system, by just changing the simple connection uh, of the variable reactor. You don't need two different test transformer. You need also you don't need two reactors. It's a question of just the connection of the reactors. On the right hand side of the figure, variable reactor which is tuned automatically of the in automatically to the desired value of the capacitive load. This is showing a variable reactor. This is the reactor as you see here, variable reactor, which can automatically set its value to the desired value for achieving resonance. Such apparatus, as I was mentioning, have come up, and as soon as you apply increasing the voltage, the voltage waveform would be sensed, and the tuned automatic reactor would set its value to the desired value to get the resonance conditions, so that you deliver, the test set is required to deliver only the real power, and the capacitive reactance of the load is balanced by the inductive reactance of the automatically tuned reactor in the laboratory itself. So such things have been developed lately. So that has given a big relief for the power cable manufacturing units to test long lengths of power cables. So that is the tuned, automatically tuned resonant circuit, as I was talking. That is the tuned resonant circuit, and automatic tuned resonant circuits is the latest development, is available in the market. Yeah. What is the advantages of the? What are the advantages of the? Just a minute. Yeah. What are the advantages of resonance transformer test set? As you can read it here, it is interesting that you should, the concept must be there in your mind. Dimensions and weight, the heavier weight of such test sets are much smaller as compared to untuned transformer delivering total capacitive current. The magnitude of the current would be very high, the conductors must be thicker, and the size also increases of the whole set. 100% compensation of capacitive reactive power is possible. And totally tuned, that means the resonant circuits are possible. Under this condition, the only power drawn from the mains or delivered by the test transformer would be the active power requirement, real power requirement, which is actually not very high, because the the conductor, suppose it is being done for the cable, conductor at the far end of the cable is at open circuit. So the real power requirement would be very, very small. There would be some very small real power requirement by the insulation. How do you estimate that real power required by the insulation? We have also learned the tan delta, the dielectric loss factor, which gives you the ratio between the reactive and the real real and the reactive power, the ratio. So it is very small actually. So the tan delta gives, if you know the tan delta of the insulating material, you can estimate the real power consumed by the dielectric, and that is what would be required under this condition, which is very, very small. The magnitudes of the short circuit currents in case of insulation failure are minimized. When you see, when you test any apparatus with high voltage, there is always a possibility that the insulation under the test voltage gives up. It has not been given properly. I mean, it has not been brought over the conductors properly, and that is what you are actually testing. There should not be a short circuit in the insulation, or insulation failure should not take place. But it does happen if there is any flaw in bringing the insulation around the conductor, that the short circuit takes place under the test conditions. And any short circuit to the ground would draw very high current. So one must check the magnitude of the short circuit current if it happens. So the magnitudes of the short circuit currents in case of insulation failure under the resonant conditions are minimized, and that is a big need. Otherwise, if the apparatus producing the high voltage has very high current flowing through it, it can damage even the apparatus. The test apparatus can also be damaged. So the voltage wave shape is improved by attenuation of harmonic components already in the power supply. There may be some harmonic components in the power supply, and the voltage wave shapes would improve under the resonant conditions. A practical figure of the amplification of the fundamental voltage amplitude at resonance is between 20 and 50 times. A practical figure for the amplification of the fundamental voltage amplitude at resonance is between 20 and 50 times. The higher harmonic voltages are divided in the series circuit to a decreasing proportion across the capacitive load. Good wave shape helps accurate high voltage measurement, and it is very desirable when you make use of certain instrument, that is like sharing bridge. That means the harmonic effect of the power frequency wave shape is minimized because under the resonance conditions the harmonic effects will be minimized, and good wave shape helps to for accurate high voltage measurement. You can also imagine that under the tuned conditions, under the tuned conditions, when you, the tuned sets physically don't equate the reactor and capacitance. They equalize the capacitive reactance with the inductive reactance by changing or by increasing the frequency. When the frequency is increased, the would uh, capacitive reactance would go down, and the inductive reactance would increase, isn't it? XL is equal to omega C. XL will uh, increase directly proportion to the frequency, and the capacitive reactance 1 upon omega C is inversely proportional to the frequency. So you can tune the XL, you can equalize the XL and XC to the desired value. And under the high frequency, you can imagine the amplification of the fundamental voltage amplitude at resonance is between 20 to 50 times. There is a lesser effect of harmonics because of the high frequency. The power required from the supply is lower than the kVA in the main test circuit. It represents only about 5% of the main kVA with unity power factor. At high capacitive power factor, when the high magnitude of the capacitive current is being drawn, the kVA would increase. kVA, V is the same. If V is the same, A is very high, the amperage is very high. So when it is drawing only the capacitive current, the kVA requirement would be very high. But when it is drawing only the resistive current or the real power, the requirement of amplitude of the current would go down. So the total requirement of kVA, the power rating of the test set, would go down, and that reduces only to 5% of the main kVA with unity power factor. And that's a very big advantage. Then there is one disadvantage also, that the disadvantages are that the requirements of additional variable choke, some people call the reactor to be also choke, capable of withstanding the full test voltage and the full current rating. You need a reactor which can withstand the full test voltage and the full test current magnitude. So that is, you can say, is a slight disadvantage. Otherwise, the tuned resonant circuits are of great importance. I'll show you the latest production of such test unit by a very reputed company. I'll show it to you tomorrow. So and tomorrow onward, we will also, in the next lecture, we will be talking also about the one by one, the high DC voltage generation, and then high impulse voltage generation, and then in the last lecture of this chapter, high current generation we'll also talk about. So there will be 3 more lectures in this chapter, and let's make a break for today, and we will meet